Hello friends, I welcome you all on my YouTube channel Rasayan Setu. So friends, in today's video we are going to discuss previous year questions of coordination chemistry which was asked in IIT-JAM 2019 exam. Okay, so let's start. Now see, this is your first question and it says the correct order of wavelength lambda max of the halide to metal charge transfer band of, and we have three complexes in which you see that the cobalt central atom and 5 ammonia ligands are all common in your three complexes, and the difference is the ligand of halide ligand. In first it will be chlorine, in second it will be bromine, and third it will be iodine. So we want to find the order of ligand to metal charge transfer spectrum wavelength. Okay, and we have four options, that is A, B, C, D. Understand friends? Okay, so let's do the solution of this question. See, as we want to solve this question, we must have first the idea about your spectrochemical series, and you know your spectrochemical series tells about the strength of ligands. Okay, so according to your spectrochemical, as you seen in your these complexes, first, second and third, you must find first the order of ligand strength of these halide ions which are present in your metal complexes, that is chlorine, bromine and iodine. So according to our spectrochemical series, the strength of ligands, the strength of ligands follows the order. So what is the order? Is Cl minus is greater than Br minus and is greater than I minus. Okay, so this is a ligand field strength order of these ligands, that is chlorine is stronger than bromine and bromine is stronger than iodine. And we also know that the value of CFSE, that is crystal field stabilization energy, is directly related to field strength. Okay, it means when the ligand strength is high, the complex have high CFSE. Okay, so as you seen in this order, the value of CFSE is same for these complexes. So we know our CFSE is directly proportional to or directly related to field strength. Okay, so CFSE of complex containing Cl minus ligand is highest compared than Br minus or I minus. So CFSE of complex containing Cl minus is highest than Br minus or I minus. Understand? So first we find the relation between ligand field strength and CFSE. Now we know that the relationship between your energy and wavelength is given by del E is equals to Hc upon lambda. So from this relation we can conclude that your energy difference can be inversely proportional to your wavelength. It means when there is a high value of energy, the value of wavelength will be lower. Okay, and you also know that CFS is also a form of energy. This is a crystal field stabilization energy. Okay, so it means your CFSE will also inversely proportional to your lambda or lambda max. So it means those complexes which have high CFSE value will be lower lambda value. Those complexes which have high CFSE value will be at lower lambda value. Understand, friends? So we know, so we can conclude our above relation that the value of CFSE will be higher in your Cl minus complex, so its lambda will be lowest. Okay, so according to this relation, the order of lambda max will be given by C. CONH3 whole 5 iodide 2 plus is greater than CONH3 whole 5 Br2 plus is greater than CONH3 whole 5 Cl2 plus. Understand, friends? And in your question it will be your complex third, it will be second, and it will be first. So your order of lambda max will be third is greater than second is greater than first, or first is less than second or less than third, which is your option number B. See in corner. Understand, friends? Okay, so for finding lambda max you must know the value of CFSE, and for the value of CFSE you must know the order of your spectrochemical series or ligand field strength. They can be correlated to each other. Okay, so this is your question, this is your solution of this question. Now we move towards our next question, and see, it says the correct trend in the rate of substitution of Cl minus by pyridine in the following complexes. And we have 4 complexes, that is first, second, third, fourth, and we must find the order in these complexes of substitution of Cl minus by pyridine. Okay, and we have 4 options as you seen in your question, that is A, B, C, D. Understand, friends? Okay, now we solve the we do the solution of this question, and see, as we can study the substitution of Cl minus by Pi minus. So here we are square planar complexes, we have square planar complexes in this question, and in square planar complexes when you study a substitution of any ligand, here the concept of trans effect arises. So in square planar complexes you must know about the concept of trans effect, or in these complexes we consider trans effect. Okay, so according to trans effect, the trans group to chlorine with the highest trans effect among them will show the highest rate of chlorine substitution. So here what can I say? I can write it. So in these complexes, the trans group to chlorine with highest trans effect among them will show the highest rate of Cl minus substitution. Now what can I say, friends? See, as you read this statement, I say that trans group to chlorine. Here chlorine is that ligand which can is substituted, which can be substituted. Okay, so those ligand which can be substituted, we consider transposition of this ligand. Here we consider the trans groups of chlorine. Okay, and those group which have highest rate which have highest trans effect among them, so highest rate of chlorine substitution. So first we know about your the trans effect order. Okay, we must find firstly the trans effect order of all these groups. So first of all, when you see your all complexes, see your first complex in question, that is Cl CH3. This is your first complex. In second complex, okay, in third complex, and in fourth complex we have this. Okay, so what can I say? I'll say that you can consider a trans group to chlorine. So in first complex we see that trans group from chlorine is CH3. In second it will be phenyl group. In third it will be chlorine, and in third it will be hydrogen. So we have four groups in all four options. So first you must find the trans effect order of these groups. So according to your trans effect series, the trans effect order will be, see, hydrogen is greater than CH3 is greater than phenyl is greater than chlorine. This is the trans effect order, and we say that the ligand which show highest trans effect order among them will show the highest rate of chlorine substitution. So here highest rate of chlorine substitution is given by your in this complex in which the hydrogen is trans to chlorine, because it will be highest trans effect order, and after that CH3, then C6H5, then last one is chlorine. So your rate of chlorine substitution by pyridine among these complexes will be given by the order is given by fourth is greater than first is greater than second is greater than third. Okay, so according to this, your option number A, see in your corner, your option number A is the correct answer for this question. Okay friends, so in these type of question friends, you must know about the trans effect series. Okay, then you can solve this question. Understand friends? Now we can move towards our next question, and see it says the observed magnetic moments of octahedral Mn3 plus Fe3 plus and CO3 plus complexes are 4.94, 6.06 and 0.00 Bohr magneton respectively. The correct option for the electronic configuration of Mn3 plus Fe3 plus and CO3 plus metal ions in these complexes respectively are, okay, and we have four options friends, A, B, C and D. Okay, so let's do the solution of this question. See, we have given values of magnetic moments of these metal ions 4.94, 6.606 and 0.00 more magneton. Okay, so first we talk about your formula of magnetic moment. It will be given by, you know, that is mu is equals to under root n into n plus 2. Okay, Bohr magneton, where n is your number of unpaired electrons. So if you know the number of unpaired electron in any complex, you must find the value of your magnetic moment of these complex. Understand? Okay. So first we have the value of Mn3 plus. First you know that in Mn3 plus and the electronic configuration of Mn3 plus is your D4, 3D4. Okay. So possibility of unpaired electrons are 4 here. Okay. And we have value is 4.94. So the value of mu according to this configuration is n, that is 4 into 4 plus 2, that is under root 4 into 6, which is equals to under root 24. And you know under root 24 is nearly equals to 4.98, less than 5, which is given in your question. So it has 4 unpaired electrons with electronic configuration of T2G3 Eg1. Okay, because we have octahedral complexes, and because of how can we find T2G3 Eg1? Why we not consider T2G4? Because here we can observe that 4 unpaired electrons, the given value of your observed magnetic moments according to your 4 unpaired electrons, and if you consider T2G4, then then 2 electrons must be in paired condition. So it has only 2 unpaired electrons, which is not possible according to your given condition. Okay, so in this condition it's the only possible electronic configuration is T2G3 and Eg1. Now in Fe3 plus, the electronic configuration is 3d5. Okay, so according to this condition, your magnetic moment will be 5 into 5 plus 2, that is under root 5 into 7, which is equals to under root 35. Okay, so under root 35 will be nearly equal to 6.06 according to your question. Okay, so it means according to your question it has 5 unpaired electrons with electronic configuration T2G3 Eg2. Here you can also relate why we consider T2G3 Eg2 not T2G5, because here 5 unpaired electron condition according to your given value in question, given magnetic moment value in question. Okay, so the electronic configuration of Fe3 plus is T2G3 Eg2. Now in your CO3 plus have electronic configuration 3d6. Okay, and the electronic configuration of 3d6 is this type. See, so it means it has 4 unpaired electrons. So the value of your magnetic moment will be under root 4 into 4 plus 2, under root 24, which is nearly equal to 4.98. But in your question it will be 0.00. So it means there will be no unpaired electron present in your cobalt 3 plus ion. And according to this condition, the electronic configuration, the acceptable electronic configuration is what in which your all electrons will be in paired condition. That is, all 6 electrons will be in paired condition. And in this condition, the unpaired electron is 0. And because of this, the value of your magnetic moment will also consider as a 0 values. So here the electronic configuration will be equals to your T2G6 Eg0. These orbitals are T2G, these are Eg. Okay, so in your given condition, the value of the electronic configuration of Mn3 plus is T2G3 Eg1, Fe3 plus is T2G3 Eg2, and cobalt 3 plus is T2G6 Eg0. So your option number C is the correct answer according to this condition. See in your corner, option number C can relate these conditions. Okay, So I hope you understand it. See, okay, now we move towards our next question. And see, it says the value of n for the complex FeCO whole full SiMe 3 to the power n satisfying the 18 electron rule is. Okay, so here you can put the value of n. We must find the value of n, and we have the complex which satisfy the 18 electron rule. Okay, now let's do the solution of this question. See, we have a complex that is FeCO4 whole 4 in tetramethylsilane as a ligand to the power n. So here you can find the valency of complex, that is n is the valency of complex. Okay, so now friends, as in our condition which will give us in question, that is it follows 18 electron rule, means this complex has 18 electron in its valence shell. Understood? Now we can count the electron contribution of each of metal and ligands. Now we can know that one carbon monoxide ligand will contribute 2 electrons. So here 4 carbon monoxide ligand present, so it will contribute total 8 electrons. Okay, and 1 electron can be donated by your tetramethylsilane ligand. So here 8 plus 1, we have 9 electrons by ligands, and because this follow 18 electron rule, so how much electron left here? It means the Fe can donate 8 electrons. So 8 plus 8 16 plus 1 17. Okay, because of that Fe have 8 electrons in their valence shell, that is 3d6 4s2 electronic configuration of Fe. So Fe has 8 electrons by CO ligand, 1 electron from tetramethylsilane, and it plus minus n will be equals to 18. Here you can balance this 18 by the value of n. Okay, so we have 17 electrons plus minus n is equals to 18 according to this condition. So if we add 1 electron, then it must be value 18. Okay, so it means the complex has extra 1 electron, then it follows 18 electron rule. So it means the complex have minus 1 charge. The value of n is minus 1. Okay, why? Because when it have minus 1, the value of electrons will be total 18, because 17 has its own electron. Now it has minus 1 charge, then 17 and electron will be carry minus 1, so 17 plus 1 will be 18. So the value of n will be minus 1, not plus 1. Remember friends, if you place plus 1, so it means you can the complex lose 1 electron if the value of n is plus 1. So here the total value of 16, but when you place minus 1, the complex, it means the 1 electron extra on complex. So 17 plus 1 is 18 electrons total. So the value of n is minus 1. Understood? Okay, now we move towards our next question. And see, it says the true statements regarding the brown ring test carried out in the laboratory for the detection of NO3 minus is or are, and we have 4 options A, B, C, D. Okay, so friends, this is a multiple select question, friends, remember, and in multiple select question you know very well that we should select more than one option as a correct answer. Okay, and we have a 4 option, that is brown ring is due to the formation of iron nitrosyl complex. Concentrated nitric acid is used for test. The complex formed in the reaction is FeCN5NO to the power 2 minus, and the brown color complex is paramagnetic in nature. Okay, out of these 4 options you can select which one is right. Okay, so let's do the solution of this question. See, Friends, a brown ring test is performed to detect the presence of nitrate ion in solution. It is a very frequently used test by us in our laboratory test for testing of nitrate ion in our solution. Okay, so first we write that your brown ring test is performed to detect the presence of nitrate ion in the solution. Presence of nitrate ion in solution. Okay, now we must talk about the chemistry behind this experiment or behind this test. What is the chemistry we used behind this test? Okay, so first we add iron sulfate in +2 state, okay, in solution of nitrate. So a solution containing nitrate, we add iron sulfate in which iron is in +2 oxidation state. Okay, so first we add iron sulfate in solution of nitrate, and after that what will we do? Then after we slowly adding concentrated H2SO4 on the walls of test tube, then slowly adding concentrated H2SO4 on the walls of test tube. Okay, so this is the whole process which we will do in this test. First we add iron sulfate, then we add concentrated H2SO4 on the walls of test tube. Now what happen after this? And we see that in this test the acid forms a layer below the aqueous solution. Okay, and brown ring will form at the junction of two layers. This is a result or observation of this test. So what will we observe? We observe that in such that uh, the acid forms a layer below the aqueous solution. Okay, below the aqueous solution, and brown ring will form at the junction of two layers, and brown ring will form at the junction of two layers. This is the process which will we do. This is our observation, a brown ring formation. Now what happen in this process, or what chemical reaction happen in this process? I can write that in the overall reaction is the reduction of nitrate ion to nitric oxide. Okay, so the overall reaction is the reduction of nitrate ion to nitric oxide. See, nitrate ion to nitric oxide by iron second, in which iron second is oxidized to iron third, which is oxidized to iron third, followed by formation of iron nitrosyl complex. This is the whole chemistry of your this ring test. Okay, reduction of nitrate to nitric oxide by iron second oxidized into iron third and followed by the formation of iron nitrosyl complex. So these three main events will happen in this reaction. What is first is reduction of nitrate to nitric oxide, second is oxidation of iron second to iron third, and third one is formation of iron nitrosyl complex. Understand, friends? Now we can write these all processes in the form of your chemical reaction. See, we have a nitrate ion, that is NO3 minus, in a solution. Here we say that we can add FeSO4, okay, that is iron sulfate. Here iron is in plus 2 oxidation state, and slowly we can add the H2SO4 acid, okay, on the walls of test tube. This is the first process. Here we observe that your NO3 minus will convert into NO, that is nitric oxide, and your FeSO4 will convert into Fe2SO4 whole thrice plus 4H2. Now what happened in this condition, friends? See carefully. Here we see that NO3 minus will convert into NO. This is the reduction reaction, and here Fe2 plus will convert into Fe3 plus. This is the oxidation reaction. Okay. So here oxidation and reduction happen simultaneously, which is a type of redox reaction. And you can also say that iron second oxidize into iron third followed by formation of iron nitrosyl complex. So in next step your FeH2O whole 3 plus 2 plus SO4. This complex will react with your nitric oxide and convert it into your iron nitrosyl complex. See this in the 2 plus and SO4 plus H2O. This iron nitrosyl complex is a brown ring which is formed on a junction of your acid and aqueous solution. Okay, so in your brown ring the iron is in plus 2 oxidation state. See, okay, so friends, when first we observe our options, see the option 1 is brown ring is due to the formation of the iron nitrosyl complex. So this is a iron nitrosyl complex, here iron and nitrosyl ligand present. So option number A will correct answer. Okay, now see option number B. The concentrated nitric acid is used for the test. No, this is a wrong option because we use H2SO4, not nitric acid. And the third option is the complex formed in a reaction is FeCN5NO2. This is again a wrong option because we see that we have a iron nitrosyl complex, okay, not iron cyanide complex. So this is iron nitrosyl. So option number C also correct. Now we can check that option number D is right or wrong, which is say that iron nitrosyl complex or brown color complex is paramagnetic in nature or not. So for observation that this complex is paramagnetic or diamagnetic, we see that in your brown ring the iron is in plus 2 oxidation state, and in plus 2 oxidation state its electronic configuration will be 3d6, and here you can see that these H2 and NO are weak field ligands. So in 3d6 state its electronic configuration is this type. See, okay, and here because of your weak field ligand there is no pairing occurs, so its electronic configuration will be T2G4 Eg2. See, this is T2G electron, these are Eg, so T2G have 4 and Eg have 2, And ultimately we can observe that in this complex iron 2 plus have 4 unpaired electrons. So it has 4 unpaired electrons. And you know very well in coordination geometry the complex which have any single unpaired electrons or many unpaired electrons have paramagnetic in nature. Okay, so here your brown ring or iron nitrosyl complex are paramagnetic in nature. Understand? Okay, so your option number D will also correct. So in your multiple select question, your option A and D is the correct answer. A says brown ring is due to the formation of iron nitrosyl concept, which is a right answer, and D option says the brown color complex is paramagnetic in nature, which is also your right answer. Understood, friends? Okay, so this is your solution. सो फ्रेंड्स ये थे आपके सॉल्यूशन जो आपके IIT JAM 2019 में आपके कोऑर्डिनेशन केमिस्ट्री टॉपिक से पूछे गए थे. आई होप आपको समझ आए होंगे. फिर भी किसी भी तरह की डिफ़िकल्टी आए तो कमेंट सेक्शन में आके ज़रूर पूछिए फ्रेंड्स. सो थैंक यू फ्रेंड्स, थैंक यू फॉर वॉचिंग.